So thinking about the general shape of a hyperbola, whether it's horizontally or vertically arranged, we can see that they're kind of diagonal lines. They don't really exist, they're not really there, but they sort of tell us about what the equation is trying to do. Because if we're looking at what happens along those lines, you can see that our equation, the values of it, the graph, we'll try and get very, very close to it, but it's never going to actually equal that line. So that line tells us a bit about what the function is trying to do, but it also is a bit of an invisible barrier that the function can never cross. And that sort of behavior is a thing called an asymptote, where there's a very exacting definition for what an asymptote is, but for our purposes, really what we need to understand is an asymptote defines a set of values that our equation will try to be but never actually equal.
You shall not pass!
And I'll leave it to you to verify for these two cases why that can't happen, but, well, you'll see when you look at it that if you try and plug those exact things in there, you're going to end up with some equalities that can't happen. But anyway, for our two types of hyperbolas, we have two types of asymptotes that we can describe. For horizontal hyperbolas, we have asymptotes of form y equals plus or minus b over ax. So a diagonal line where now we are using that value b to tell us something about a position in terms of an imaginary thing that's kind of hard to see because it's not really there, but that tells us something important about what we're trying to do. And then similarly for the vertical case, we have plus or minus a over bx. So it's the same sort of thing, but flipped over, which makes sense because, well, the horizontal and vertical distinction is really just a matter of rotation. They should have similar asymptotes. Where again, we should understand that these lines, they're not actually a part of the graph, they're not actually a part of the equation, but they are very informative in terms of what the equation does. And in fact, we can use these to be able to generate rough graphs for our hyperbolas using a few steps, where what we do is we locate the vertices of the hyperbola. That is, we figure out what the value a is, what the transverse axis is, and how far away things have to be from the center. Then we draw dashed lines to make a rectangle centered at the origin or wherever the center of the hyperbola is, parallel to our axes, crossing one at plus or minus a and the other at plus or minus b. So we're kind of making a box around the middle that's going to tell us essentially where the vertices are. And then from there, we draw the diagonals through the rectangle and use that to make our asymptotes. And then we draw the branches of the hyperbola starting at the vertex, each vertex that is, the two vertices, and approaching those asymptotic lines. Where, to understand this, like always, we're going to take an example. So for this example, we want to graph and find the foci of x squared over 36 minus y squared over 9 equals 1. Well, for this, the first thing we should note is that because we have the positive coefficient with x, that is x is first in the standard arrangement, we are going to be looking at things in terms of the horizontal arrangement. So, at the very least here, without thinking too hard about that, we have that a is equal to 6. And if we want to find our vertices, since we are working from the center, those will be at plus or minus 6, 0. Okay, it's not so bad, not so hard to find the vertices. The next step is a little bit trickier. So what we're going to do for that next step is we're going to take our values a and b and kind of use those to make a rectangle where the rectangle has, in this case, width defined by a and height defined by b. If we flipped the arrangement and had y first, we would have height for a and width for b, but you'll see that in practice as well. So here we have that a is 6 and b is 3. So we're going to draw ourselves a dashed rectangle essentially around that center, making sure to hit our vertices with width 6. Excuse me, not width 6, it's width 12 because it's 2 copies of 6, and then height with 2 3s or 6. It's so nice when you have those numbers line up just right to be a little confusing, isn't it? But anyway, from there what we do is we take our rectangle and we make our diagonals, where our diagonals there are what will represent the asymptotes. So we're just going to draw those through and then keep them going all the way out. Once we have all of those pieces in there, we can then talk about what's going on, where, just to be clear, if we want to know what those asymptotes are, they will have form y equals plus or minus b over a, x in this case, because it is the horizontal arrangement, which here is plus or minus 1/2 x. But the big thing is we could take this picture here and fill in something like our hyperbolas, although in this case those parabolas they're a little wimpy for this. So they're a little small, but the scale necessitates that smallness. And we end up with a picture something like so, where if we wanted to get our foci in particular, we would have that c squared is going to be equal to 36 plus 9. So our foci are going to be at plus or minus, not very nice number, root 45, comma 0. I guess that's not always nice, it's very rarely nice. But this is our process here, and the next thing we can think about is how we would look at these things in more general terms.